Beneath the endless blue of Earth's skies, a silent giant burns. Its light has nourished every forest, every ocean, every living cell that has ever drawn breath. Civilizations rose beneath its warmth, tracing its path with stones aligned to solstices, building temples to honor its fire. To the ancients, the sun was more than a star. It was the heart of creation itself, a god suspended in the heavens, steady and eternal. Yet within its brilliance hides a darker truth, one that no myth could ever capture. For this star is not only the giver of life, but also its most patient destroyer. The sun is not calm, though it seems so to the eye. Beneath its golden face lies a churning sea of plasma, magnetic fields coiling and snapping in violent arcs. In moments unseen by human vision, the surface can erupt, flinging storms across the void. Invisible rivers of charged particles surge outward, racing toward the planets. To us, it seems distant, untouchable. But when these tempests find Earth, they strike at our very foundations. Our planet carries a fragile shield, a magnetic cocoon spun from its molten core. Against the sun's fury, this field stands like a wall of glass against fire. Most days, it bends the storm, sending the streams of particles flowing harmlessly past. But sometimes, when the sun's rage flares too bright, that wall shudders. Auroras ignite across the night sky, emerald and crimson curtains of light, dancing as if the heavens themselves are burning. They are beautiful, yet they are warnings, silent signals that the sun has touched us. In an age before electricity, these storms were omens. To those who watched the skies, they were visions of gods at war. But today humanity has bound its survival to invisible threads of power, satellites in orbit, global networks pulsing with data, power grids stretching across continents. The storms that once painted the night sky could now tear through the arteries of our civilization. A great eruption from the sun, one stronger than any in living memory, could hurl billions of tons of plasma toward Earth. In hours, it could overwhelm the magnetic field, disrupt satellites, cripple communications, and plunge cities into darkness. Nuclear war has long haunted humanity as the symbol of its own potential end. Yet the bombs of nations are sparks compared to the furnace of our star. Humanity built its weapons in decades. The sun has been shaping and unmaking worlds for billions of years, and it needs no malice, no intention. Its fury is simply nature, burning without thought, without pause. The question lingers like a shadow across the light. What would happen if tomorrow the sun unleashed a storm vast enough to test the limits of our fragile world? Would our machines endure? Would our defenses hold? Or would the star that gave us life remind us, in a single blinding instant, that we remain at its mercy? The mystery is not whether the sun will erupt again. It is when, and in that waiting silence, scientists search the light, measuring, watching, listening to the heartbeat of a star, wondering if the greatest fire we fear does not lie in the weapons of man, but in the eternal blaze above. In the middle of the 19th century, as telescopes swept their glass eyes across the heavens, a quiet revolution began. The sun, long regarded as steady and unchanging, revealed its first violent secret. On September 1st, 1859, a British astronomer named Richard Carrington traced a cluster of dark sunspots through his telescope. Suddenly, before his astonished gaze, a brilliant flash erupted, a burst of white light so fierce it seared itself into the page of history. He could not know it then, but Carrington had witnessed the first recorded solar flare. Within hours, the Earth itself would tremble beneath its reach. Across the Atlantic, telegraph operators struggled as their machines sparked and burned. Lines meant to carry words began carrying fire. Reports spoke of instruments bursting into flame, of shocks that threw operators back from their desks. Auroras bled across the skies, no longer confined to the polar circles. Curtains of red and green light draped the heavens as far south as the Caribbean, glowing so bright that miners in Colorado claimed they could read newspapers beneath the night sky. To those who looked up, it was as though the atmosphere itself had been set ablaze. The Carrington Event shattered the illusion that the sun was a constant, gentle beacon. It revealed a hidden violence. Eruptions of plasma hurled across 93 million miles of space, striking Earth like an unseen hammer. Humanity had stumbled into the reality of space weather, though it would take more than a century to give this force a name. The age of heliophysics had quietly begun. Born from a storm that few understood, for generations, these eruptions were little more than curiosities, their causes wrapped in mystery. Astronomers tracked sunspots, sketching their dark blemishes as they swirled across the solar disk. They began to see patterns, an 11-year cycle of activity, a rhythm of unrest and calm. Yet the underlying mechanism remained elusive, a puzzle of magnetism and plasma no earthly experiment could fully imitate. Still, each glimpse deepened the sense that the sun was not the stable constant it appeared, but a restless giant dot in the modern era. New eyes were lifted toward the star. Orbiting sentinels, free from Earth's distortion, began to watch the sun in wavelengths no human eye could see. The Solar and Heliospheric Observatory, launched in 1995, caught the sun in constant vigil, recording eruptions in their first moments. The Solar Dynamics Observatory painted its atmosphere in ultraviolet, revealing arcs of plasma that rose like mountains, then snapped into storms that dwarfed the Earth itself. And most daring of all, NASA's Parker solar probe dove closer than any craft in history, brushing the edges of the sun's corona, flying into the furnace to hear the heartbeat of fire. What they revealed was staggering. Loops of plasma hundreds of thousands of kilometers high, explosions releasing the energy of billions of nuclear bombs, blasts so vast they could hurl entire clouds of matter into interplanetary space, traveling at millions of kilometers per hour. To see such events unfold in real time was to confront both awe and dread. The sun was not simply a warm presence in the sky, it was a roaring furnace, its surface alive with storms capable of unmaking the fragile machines of human civilization. And yet, amid this growing knowledge lies the deeper mystery: prediction. Those satellites trace the dance of magnetic fields, those simulations run on the world's most powerful computers, the precise timing of the next great storm eludes science. The sun continues to erupt without warning, its tempests racing across space while we look upward. Uncertain, the story of solar observation is not just one of discovery, but of humility. Each breakthrough, from Carrington's blinding flare to Parker's daring plunge, reminds us that we are children beneath a star whose moods we do not command. We listen, we measure, we watch, but the sun remains vast, restless, and sovereign. In its storms lies both beauty and terror, a reminder that the same fire that sustains life carries within it the power to disrupt everything humanity has built in the middle of the 19th century. As telescopes swept their glass eyes across the heavens, a quiet revolution began. The sun, long regarded as steady and unchanging, revealed its first violent secret. On September 1st, 1859, a British astronomer named Richard Carrington traced a cluster of dark sunspots through his telescope. Suddenly, before his astonished gaze, a brilliant flash erupted, a burst of white light so fierce it seared itself into the page of history. He could not know it then, but Carrington had witnessed the first recorded solar flare. Within hours, the Earth itself would tremble beneath its reach. Across the Atlantic, telegraph operators struggled as their machines sparked and burned. Lines meant to carry words began carrying fire. Reports spoke of instruments bursting into flame, of shocks that threw operators back from their desks. Auroras bled across the skies, no longer confined to the polar circles. Curtains of red and green light draped the heavens as far south as the Caribbean, glowing so bright that miners in Colorado claimed they could read newspapers beneath the night sky. To those who looked up, it was as though the atmosphere itself had been set ablaze. The Carrington Event shattered the illusion that the sun was a constant, gentle beacon. It revealed a hidden violence. Eruptions of plasma hurled across 93 million miles of space, striking Earth like an unseen hammer. Humanity had stumbled into the reality of space weather, though it would take more than a century to give this force a name. The age of heliophysics had quietly begun. Born from a storm that few understood, for generations, these eruptions were little more than curiosities, their causes wrapped in mystery. Astronomers tracked sunspots, sketching their dark blemishes as they swirled across the solar disk. They began to see patterns, an 11-year cycle of activity, a rhythm of unrest and calm. Yet the underlying mechanism remained elusive, a puzzle of magnetism and plasma no earthly experiment could fully imitate. Still, each glimpse deepened the sense that the sun was not the stable constant it appeared, but a restless giant. In the modern era, new eyes were lifted toward the star. Orbiting sentinels, free from Earth's distortion, began to watch the sun in wavelengths no human eye could see. The Solar and Heliospheric Observatory, launched in 1995, caught the sun in constant vigil, recording eruptions in their first moments. The Solar Dynamics Observatory painted its atmosphere in ultraviolet, revealing arcs of plasma that rose like mountains, then snapped into storms that dwarfed the Earth itself. And most daring of all, NASA's Parker Solar Probe dove closer than any craft in history, brushing the edges of the sun's corona, flying into the furnace to hear the heartbeat of fire. What they revealed was staggering. Loops of plasma hundreds of thousands of kilometers high, explosions releasing the energy of billions of nuclear bombs, blasts so vast they could hurl entire clouds of matter into interplanetary space, traveling at millions of kilometers per hour. To see such events unfold in real time was to confront both awe and dread. The sun was not simply a warm presence in the sky. It was a roaring furnace, its surface alive with storms capable of unmaking the fragile machines of human civilization. And yet, amid this growing knowledge lies the deeper mystery, prediction. Though satellites trace the dance of magnetic fields, though simulations run on the world's most powerful computers, the precise timing of the next great storm eludes science. The sun continues to erupt without warning, its tempests racing across space while we look upward. Uncertain, the story of solar observation is not just one of discovery, but of humility. Each breakthrough, from Carrington's blinding flare to Parker's daring plunge, reminds us that we are children beneath a star whose moods we do not command. We listen, we measure, we watch, but the sun remains vast, restless, and sovereign. In its storms lies both beauty and terror, a reminder that the same fire that sustains life carries within it the power to disrupt everything humanity has built. Beneath the surface of the sun lies a vast, shifting engine, a sphere of nuclear fire that resists stability. Its plasma flows like rivers of light, twisting under forces so immense they defy intuition. Magnetic lines writhe, snap, and reconnect, flinging arcs of energy outward in sudden bursts. Scientists call this process magnetic reconnection, a cosmic act of rupture that transforms invisible tension into storms stretching across millions of kilometers. To imagine it is to picture the Earth swallowed in a single flare, reduced to a speck against the sheer scale of the violence above. The difficulty lies not in recognizing that the sun erupts, but in knowing when. Space weather is unlike the tides, the seasons, or the turning of the moon. It resists rhythm. Its eruptions can be preceded by silence. Its storms born in tangled fields that give no warning until the very instant they break. Astronomers map sunspot cycles, tracing their 11-year rise and fall. But even these patterns are threads in a fabric too vast to weave into certainty. Prediction remains elusive, and in that uncertainty lies humanity's unease. The star above cannot be controlled, cannot be bargained with, and cannot be silenced. When coronal mass ejections surge outward, they become vast clouds of plasma threaded with magnetic fields. Each is a world-sized tempest drifting through interplanetary space. Some wander harmlessly into the void, dissolving into darkness. Others cross paths with Earth, where the magnetosphere awaits like a fragile shield. When impact comes, it is not sound or flame, but a silent compression, a shudder that rattles the very fabric of the magnetic cocoon. In those moments, entire continents are vulnerable. Evidence of past encounters lingers in unexpected places. Ice cores from Greenland and Antarctica hold traces of ancient solar storms, revealed in sudden spikes of radioactive isotopes. These frozen records tell of events that dwarfed even the Carrington storm, eruptions that left chemical scars in Earth's atmosphere centuries before telegraphs or satellites existed. What those storms would do to modern infrastructure remains an open question. Some models suggest blackouts stretching across continents, satellites falling silent, and communication systems collapsing in cascades of failure. The sun, through a single act, could throw civilization into shadow, yet the possibility of something even greater lingers at the edge of speculation. Superflares witnessed on stars much like our own radiate energy that exceeds the Carrington Event by factors of 100 or more. Observatories such as Kepler have recorded their light sudden, catastrophic brightening that reshapes the understanding of stellar behavior. If the sun is capable of such violence, it has remained dormant for millennia. But dormancy does not erase possibility. To imagine a superflare striking Earth is to imagine a planet bathed in radiation, satellites stripped from orbit, grids destroyed, oceans of technology silenced in an instant. It is a vision that borders the apocalyptic, yet rests upon a foundation of scientific evidence. The irony is profound. The sun's storms are born from the same processes that make life possible. Its magnetic field is the natural child of nuclear fusion, the energy source that sustains light, warmth, and growth across Earth. Without this turbulence, the sun would not shine as it does. The same magnetism that threatens to erase our machines is the magnetism that allows the star to breathe. In its chaos lies both creation and destruction, a balance that defines the paradox of existence beneath a star. Meanwhile, the aurora remains the most visible reminder of this balance. To the casual eye, it is beauty without menace, ribbons of color woven across polar skies, shimmering like the brushstrokes of gods. But each flicker marks a collision. Each glow is the footprint of solar particles crashing into Earth's atmosphere at speeds unimaginable. The aurora is a canvas painted by violence, a translation of invisible storms into light. Humanity marvels at its colors, photographs its shapes, and tells stories of spirits and ancestors moving in the night. Few pause to see what lies beneath that beauty, the echo of storms that could one day rise to silence entire nations. And so the mystery deepens. Scientists measure plasma flows, map fields of magnetism, and launch probes into the furnace, yet certainty slips from their grasp. Every discovery reveals not order, but deeper complexity, as though the sun resists being fully known. It is a reminder of humility, A reminder that even in an age of supercomputers and space telescopes, the forces that govern the nearest star remain vast and unruly. Humanity can chart probabilities, but not inevitabilities. It can prepare, but not prevent. Somewhere in the heart of the sun, perhaps already, magnetic fields coil tighter, storing tension like a bow ready to release. It may snap tomorrow or centuries from now, but the inevitability is written into the physics of a star. Storms will come. Their beauty will dazzle, their power will threaten, and their unpredictability will remain a shadow. Hanging over the fragile weave of human civilization, the danger of the sun is not its heat or its fire. It is the silence before the storm, the magnetic threads that twist unseen, the certainty that somewhere within the golden face of the sky lies the seed of an eruption vast enough to remind humanity that it has always lived at the mercy of a star. Beneath the surface of the sun lies a vast, shifting engine, a sphere of nuclear fire that resists stability. Its plasma flows like rivers of light, twisting under forces so immense they defy intuition. Magnetic lines writhe, snap, and reconnect, flinging arcs of energy outward in sudden bursts. Scientists call this process magnetic reconnection, a cosmic act of rupture that transforms invisible tension into storms stretching across millions of kilometers. To imagine it is to picture the Earth swallowed in a single flare, reduced to a speck against the sheer scale of the violence above. The difficulty lies not in recognizing that the sun erupts, but in knowing when. Space weather is unlike the tides, the seasons, or the turning of the moon. It resists rhythm. Its eruptions can be preceded by silence. Its storms born in tangled fields that give no warning until the very instant they break. Astronomers map sunspot cycles, tracing their 11-year rise and fall. But even these patterns are threads in a fabric too vast to weave into certainty. Prediction remains elusive, and in that uncertainty lies humanity's unease. The star above cannot be controlled, cannot be bargained with, and cannot be silenced. When coronal mass ejections surge outward, they become vast clouds of plasma threaded with magnetic fields. Each is a world-sized tempest drifting through interplanetary space. Some wander harmlessly into the void, dissolving into darkness. Others cross paths with Earth, where the magnetosphere awaits like a fragile shield. When impact comes, it is not sound or flame, but a silent compression, a shudder that rattles the very fabric of the magnetic cocoon. In those moments, entire continents are vulnerable. Evidence of past encounters lingers in unexpected places. Ice cores from Greenland and Antarctica hold traces of ancient solar storms, revealed in sudden spikes of radioactive isotopes. These frozen records tell of events that dwarfed even the Carrington storm, eruptions that left chemical scars in Earth's atmosphere centuries before telegraphs or satellites existed. What those storms would do to modern infrastructure remains an open question. Some models suggest blackouts stretching across continents, satellites falling silent, and communication systems collapsing in cascades of failure. The sun, through a single act, could throw civilization into shadow. Yet the possibility of something even greater lingers at the edge of speculation. Superflares, witnessed on stars much like our own, radiate energy that exceeds the Carrington Event by factors of 100 or more. Observatories such as Kepler have recorded their light, sudden, catastrophic brightening that reshapes the understanding of stellar behavior. If the sun is capable of such violence, it has remained dormant for millennia. But dormancy does not erase possibility. To imagine a superflare striking Earth is to imagine a planet bathed in radiation, satellites stripped from orbit, grids destroyed, oceans of technology silenced in an instant. It is a vision that borders the apocalyptic, yet rests upon a foundation of scientific evidence. The irony is profound. The sun's storms are born from the same processes that make life possible. Its magnetic field is the natural child of nuclear fusion, the energy source that sustains light, warmth, and growth across Earth. Without this turbulence, the sun would not shine as it does. The same magnetism that threatens to erase our machines is the magnetism that allows the star to breathe. In its chaos lies both creation and destruction, a balance that defines the paradox of existence beneath a star. Meanwhile, the aurora remains the most visible reminder of this balance. To the casual eye, it is beauty without menace, ribbons of color woven across polar skies, shimmering like the brushstrokes of gods. But each flicker marks a collision. Each glow is the footprint of solar particles crashing into Earth's atmosphere at speeds unimaginable. The aurora is a canvas painted by violence, a translation of invisible storms into light. Humanity marvels at its colors, photographs its shapes, and tells stories of spirits and ancestors moving in the night. Few pause to see what lies beneath that beauty, the echo of storms that could one day rise to silence entire nations. And so the mystery deepens. Scientists measure plasma flows, map fields of magnetism, and launch probes into the furnace, yet certainty slips from their grasp. Every discovery reveals not order, but deeper complexity, as though the sun resists being fully known. It is a reminder of humility, a reminder that even in an age of supercomputers and space telescopes, the forces that govern the nearest star remain vast and unruly. Humanity can chart probabilities, but not inevitabilities. It can prepare, but not prevent. Somewhere in the heart of the sun, perhaps already, magnetic fields coil tighter, storing tension like a bow ready to release. It may snap tomorrow, or centuries from now, but the inevitability is written into the physics of a star. Storms will come. Their beauty will dazzle, their power will threaten, and their unpredictability will remain a shadow. Hanging over the fragile weave of human civilization, the danger of the sun is not its heat or its fire. It is the silence before the storm, the magnetic threads that twist unseen, the certainty that somewhere within the golden face of the sky lies the seed of an eruption vast enough to remind humanity that it has always lived at the mercy of a star. Beneath the growing weight of evidence, the perception of the sun began to fracture. What once had been the universal symbol of stability was now revealed as volatile, unpredictable, even dangerous. Yet that realization did not arrive suddenly. It came in a slow cascade of moments, each discovery pulling humanity deeper into the truth. In the decades following Carrington's flare, the scientific community wrestled with unsettling observations. Telegraph operators had described sparks leaping from their equipment, paper igniting spontaneously, and lines carrying signals even after batteries were disconnected. The Earth itself, they realized, had become an unwitting conductor of the sun's unleashed currents. And still, no one could fully explain how or why. For many years, the storm remained a mystery, a story told in fragments, its magnitude underestimated by those who preferred to believe the heavens were distant and detached from earthly affairs. The rise of radio in the early 20th century brought a new form of vulnerability. For the first time, invisible signals bound continents together, whispering across oceans through the atmosphere. Yet strange disruptions plagued these transmissions. Bursts of static, sudden silences, voices lost in the ether. Slowly, investigators began to notice the uncanny timing of these disturbances. When sunspots peaked in number, so too did the failures of radio. The suspicion grew that the sun was not a passive backdrop, but an active force shaping the new networks of human communication. The stage was set for an era of revelation and of unease. By mid-century, Technology and geopolitics collided with astrophysics. The space race lifted instruments above the protective blanket of the atmosphere, exposing them directly to the torrent of solar radiation. Geiger counters aboard early satellites crackled with surges that rose and fell in step with solar storms. Photographic plates returned from orbit, streaked with ghostly traces of high-energy particles, silent evidence of storms that had crossed the void to strike with invisible hands. What had been anecdotal became measurable. The sun's violence was not speculation, it was data in military circles. This knowledge took on a sharper edge. During the Cold War, communication lines and radar systems formed the backbone of defense. The watchful eyes meant to guard against nuclear annihilation. Yet a powerful solar storm could blind those systems without warning, creating the illusion of an attack or the silence of a world gone dark. Documents quietly circulated through defense agencies, warning that the sun's interference could trigger catastrophic misunderstandings in an already volatile era. The enemy was no longer only human, it was a star, burning with indifference 93 million miles away. It was within this climate of suspicion and urgency that the field of space weather forecasting emerged. Scientists, armed with the growing capabilities of satellites and ground-based observatories, began to trace the patterns of solar storms. Magnetometers on Earth measured subtle fluctuations, ripples in the planet's field as waves of plasma swept past. Radio telescopes listened to the sun as though it were a transmitter, catching the static bursts of flares and the deep, slow pulses of its changing magnetic heart. Out of these efforts grew the first primitive warnings, alerts that a storm might be coming, though often too late, too imprecise to be of comfort. The pioneers of this field often worked in obscurity. They battled skepticism not only from the public, but from fellow scientists who doubted the practical importance of their findings. Yet they persisted, guided by the haunting memory of Carrington's storm and the knowledge that another, perhaps even greater, would one day arrive. Their work was not merely academic. It was an act of preparation, an attempt to shield a civilization, increasingly woven together by fragile lines of electricity and orbiting machines of silicon and steel. As the discipline matured, so too did the vision of the sun itself. No longer was it seen simply as a sphere of glowing gas. It became understood as a complex, dynamic system, a magnetic engine whose surface roared with storms and whose atmosphere extended far beyond what the eye could see. The solar wind, once invisible, now recognized as a constant river of charged particles, became a subject of intense study. Its variations, subtle and violent, connected the sun to the earth in ways more intimate than ever imagined. By the late 20th century, satellites like SOHO and instruments on Skylab provided humanity with unprecedented images, loops of plasma, arching tens of thousands of kilometers into space, prominences twisting like serpents of fire, explosions so vast they could engulf entire planets. For those who saw these images, awe was mingled with fear. The sun, once a serene symbol of light, was revealed in all its raw turbulence, and with every new discovery, the realization deepened that the greatest threat to human technology, perhaps even to modern civilization itself, did not lurk in the arsenals of nations, but in the restless heart of the star that gives us life. Thus the story of discovery stretched across centuries, from Galileo's trembling sketch of dark spots to Carrington's blazing flare, from prisms splitting light into spectral codes to satellites scarred by radiation. Each revelation carried humanity further from myth and closer to truth. The sun was not simply a giver of warmth and light. It was a stormbringer, a force whose moods shaped the sky, the earth, and the fragile web of civilization itself. And as the 20th century drew to a close, A haunting question lingered in the silence of laboratories and observatories. If the storms we had already seen could ignite fires, silence radios, and bend the Earth's magnetic field, what storms might yet come? What might lie in the hidden rhythms of a star that has burned for billions of years? And what would happen when those rhythms turned violent again? In the early decades of solar science, a strange resistance lingered in the hearts of scholars and engineers alike. The idea that the sun, the same benevolent sphere that warmed crops and lit the days of every civilization in history, could also cripple human technology seemed far-fetched, almost absurd. For centuries, the heavens had been considered immutable, distant, beyond the reach of daily life. Lightning could strike, storms could rage, earthquakes could shatter cities, but the sun, it was constant, eternal. To suggest otherwise was, too many, a step too far. This skepticism ran deep in the veins of 20th century science, though Carrington's flare had burned itself into the historical record, and though the disruptive effects of solar storms on telegraph and radio had been documented, they were often dismissed as curiosities, odd coincidences rather than patterns. Technology, it was assumed, was stronger than the whims of the sky. The wires of progress would not bow to celestial winds. Humanity, intoxicated by its rapid industrial ascent, placed faith in its machines, steel, copper, and silicon, as if they were invincible fortresses. But then, one winter night, in March of 1989, illusions collapsed. A solar storm, vast and unseen, swept down upon the Earth. In Quebec, the currents it induced in the planet's crust raced into the power grid, overwhelming systems that had never imagined such a foe. In less than 2 minutes, the entire province was thrust into darkness. 6 million people found themselves without light, without heat, without communication. The storm had crossed 93 million miles to flick a single switch, and civilization had fallen silent before it. For engineers, it was a rude awakening. The blackout was not caused by failure in design or negligence in oversight. It was caused by something far more humbling, the restless magnetism of a star. Power lines that had been built to withstand storms of weather had bent instead to storms of plasma, invisible yet unstoppable. The event was a mirror held to humanity's vulnerability, reflecting just how thin the thread of modern life truly was. And still, Quebec was not alone. In the Cold War decades that preceded it, military planners had faced their own unsettling revelations. Solar storms had been observed interfering with radar systems designed to scan the skies for nuclear threats. In a world balanced on the edge of mutually assured destruction, even seconds of blindness could be catastrophic. What if a solar flare silenced warning systems at the wrong moment? What if phantom signals were misinterpreted as enemy strikes? The sun, indifferent to human politics, became a silent, unpredictable player in the chess game of superpowers. Yet even then, disbelief lingered. Many in positions of authority resisted the notion that the very infrastructure of human civilization, satellites, power grids, radio navigation systems, could be bent or broken by something as remote as a star. To admit such a thing was to admit a fundamental weakness, to concede that progress was not a straight road to mastery, but a fragile balancing act against forces older and greater than humanity itself. Slowly, reluctantly, the evidence forced acceptance. Satellites faltered under bursts of radiation, their circuits scrambled, their guidance lost. Astronauts aboard space stations reported eerie, intensified auroras sweeping below them, electric curtains of light that shimmered as though the Earth itself were aflame. Radio operators tracked sudden silences across entire continents, their instruments overwhelmed by a deluge of charged particles. Each observation chipped away at the illusion of invulnerability. Each failure whispered the same truth. The sun was not passive. It was not benign. It was active, dynamic, and dangerous. And beneath these realizations grew something less tangible, something more philosophical. Humanity was accustomed to fearing what it could see: armies, weapons, storms, and quakes. But the threat of the sun was invisible, untouchable, an enemy without form or malice. It was a reminder that the cosmos is not designed with human fragility in mind, that civilization exists not as a fortress but as a fragile flame flickering beneath a vast and indifferent sky. Nuclear weapons might embody the fear humanity has of itself, but the sun embodies the fear of nature itself, raw and uncontrollable. In the wake of these revelations, the scientific community began to change its stance. Space weather, once a fringe concern, grew into a recognized discipline. Governments began to issue storm alerts, however imprecise, and satellites were launched not merely to observe the sun's beauty but to warn of its violence. Yet even as the systems improved, one truth remained inescapable: warnings could not prevent the storm, only soften its blow. The first scientific reactions to the sun's fury were thus not merely academic debates or technical puzzles. They were lessons in humility, lessons that progress is not invincibility, that civilization's web of wires and orbits, so powerful and so intricate, is also delicate, exposed to the same cosmic storms that once painted the sky with light over ancient temples and frightened shepherds beneath auroral fire. The unease has never truly left us, for beneath every advance, every new invention, lies the quiet knowledge that above us burns a force we cannot tame, and that one day it may choose to remind us again. The skepticism of the early 20th century had been more than intellectual hesitation. It was bound up in the pride of progress. To acknowledge that an external celestial force could interrupt the intricate machinery of modern civilization was to challenge the very narrative of control. Trains ran on timetables, factories glowed through the night, and communications spanned oceans, all evidence that humanity had finally bent nature to its will. To suggest that invisible currents from the sun could unravel these achievements seemed almost insulting, a blow to the triumph of reason over chaos. Yet the universe has a way of reminding civilizations of their place. Long before the blackout, in Quebec, there were warnings, though few cared to listen. In May of 1921, telegraph lines in New York and railway signal systems in the Northeast faltered under the weight of another solar storm. Operators reported instruments burning, fuses blown, and systems collapsing in ways no engineer had anticipated. The storm was less documented than Carrington's flare, but, in many ways, nearly as severe. Had the infrastructure of the late 20th century existed in 1921, historians now suspect it would have been catastrophic on a scale rivaling or surpassing the Quebec event. But in that age of wires and steam, the damage was survivable. The lesson, however, was largely forgotten by the 1970s. With satellites now orbiting Earth, the sun's reach became undeniable. Signals from communication satellites occasionally flickered, television broadcasts fractured into static, and early GPS systems lost precision. Engineers puzzled over the anomalies until correlations with solar activity became impossible to ignore. In 1972, a particularly violent solar storm detonated dozens of naval mines in the waters of Vietnam. Their sensors triggered not by human action, but by the electric chaos of a star 93 million miles away. It was a moment of quiet terror for military strategists, proof that solar storms could ignite conflict by accident, turning the machinery of war against its masters. The scientific community began to assemble these scattered warnings into a larger narrative. They realized that the Earth was not simply a passive world orbiting within the sun's light, but a participant in its storms. The magnetic shield of the planet, once considered unassailable, could be bent and battered by coronal mass ejections. Like the hull of a ship struck by great waves, it could hold, but only to a point. And if it bent too far, the consequences would spill into every human system tethered to electricity and orbit. Still, disbelief persisted in certain corners. Many clung to the faith that redundancy and engineering safeguards could outmatch nature. They believed that no star, however powerful, could undo human ingenuity. But the mounting evidence of failure told another story. In 1982, a geomagnetic storm disrupted radio communication with the Space Shuttle Columbia during launch. A sobering reminder that even the most celebrated achievements of space exploration were not immune. For astronauts drifting beyond the protective blanket of the atmosphere, the danger was even more personal. A powerful solar storm could bathe them in lethal radiation within hours. By the time Quebec was thrown into darkness, the pattern had become impossible to deny. The blackouts, the failed satellites, the disrupted communications, they were not isolated events. They were signatures of a deeper truth. The sun was not merely a background light, but an active force with moods and tempests, capable of touching every layer of civilization. The event marked a shift not only in engineering but in philosophy. Humanity was forced to recognize that its greatest vulnerability was not only internal, born of politics or war, but external, written into the sky itself. The first steps into the systematic study of the sun's storms were tentative, fragile, like a child learning to walk across uncertain ground. Early observatories, perched on mountaintops and scattered across continents, raised their lenses toward the brilliant disk, recording in silence the restless dance of spots, flares, and shifting light. From India to California, from Europe to South America, astronomers charted what seemed to be a rhythm, a cycle of activity waxing and waning roughly every 11 years. At first, it was little more than a curiosity, an oscillation traced in ink across ledgers and journals. But as the years stretched into decades, a pattern revealed itself. Solar storms rose and fell in lockstep with that mysterious cycle. What seemed like idle astronomy became a map of danger. Still, the tools of Earth alone were not enough. The atmosphere, protective and opaque, shielded observers from the most dangerous radiation and blurred the finest details of the sun's corona. That shimmering veil of plasma seen only in rare eclipses. To probe deeper required leaving the Earth itself, lifting instruments into space where they could stare directly into the glare of the star without distortion. With the dawn of the space age, that dream became possible. In 1973, Skylab turned its instruments toward the sun, capturing images of coronal loops and eruptions so vast they seemed almost alien, rivers of fire stretching into the void. Later, the joint efforts of NASA and the European Space Agency gave rise to SOHO, the Solar and Heliospheric Observatory. Stationed 1 million miles from Earth, from its silent watchpost, it beheld the sun in constant vigilance, recording every eruption, every pulse of activity, every storm that unfurled into interplanetary space. Each mission brought humanity closer to understanding, yet closer to unease. Spectroscopy revealed that the corona impossibly, mysteriously, was hotter than the sun's surface itself, millions of degrees boiling where logic suggested there should be cooling. Magnetic field lines twisted into knots of unbearable tension, then snapped, releasing explosions of plasma that raced across space at millions of kilometers per hour. It was clear the sun was not calm, and its storms were not rare. They were frequent, unpredictable, and often invisible until they struck. The Parker Solar Probe, launched in 2018, marked the boldest step yet, a spacecraft designed to skim the edge of the sun's atmosphere. wrapped in a carbon shield strong enough to withstand heat that could melt metal. Each orbit carried it closer, threading through the corona itself, tasting the streams of plasma that flow outward as the solar wind. Parker's daring mission was more than scientific ambition. It was necessity. Without understanding the forces at play within the corona, forecasting remained a fragile art, reliant on partial glimpses and delayed signals. To predict solar storms was to attempt reading the moods of a star with only fragments of its language. Scientists had long known that the sun moved through cycles, its magnetic fields reversing polarity every 11 years, a cosmic heartbeat of rising and falling storms. But the cycle was no clock. Its peaks varied in intensity, some blazing with violent activity, others strangely subdued, even within a single peak. Predicting which flare would erupt harmlessly and which would become a coronal mass ejection remained elusive. The sun whispered patterns, but refused to reveal its code. The stakes of this ignorance grew clearer with every passing decade. Engineers and scientists drew connections between peaks of solar activity and failures in human technology, satellites faltering, navigation systems drifting, power grids straining under invisible currents. Each cycle brought new disruptions, each disruption adding urgency. The sun was no longer a distant object of worship or myth, but a looming hazard woven into the infrastructure of civilization itself. And yet, compared to the mastery of terrestrial weather, space weather forecasting remained primitive. Meteorology on Earth could predict hurricanes days in advance, track storms across continents, and warn cities with precision. But in space, forecasters could do little more than watch and wait, offering warnings measured in minutes or hours at best. The instruments of Soho, Stereo, and Parker provided vision, but not foresight. The sun remained opaque, its hidden engines beyond the grasp of even the most advanced models. In laboratories and observatories, there was both awe and frustration. Awe at the sheer complexity of a star's magnetic ballet, frustration at the limits of understanding. Every mission uncovered new mysteries, particles accelerating to near light speed for reasons still unclear, magnetic waves spiraling through plasma-like invisible serpents, storms that seemed to arise from nowhere. The deeper scientists probed, the less predictable the sun appeared, yet the urgency to solve its riddles has never been greater. Satellites now guide aircraft, steer ships, and synchronize financial networks. Power grids knit continents together. Communications weave societies into a single fabric. The sun, indifferent as it may be, holds in its storms the power to tear those threads apart. Each new mission is a race not of nations against nations, but of a species against the silence of the cosmos. A race to understand before catastrophe strikes. And so humanity watches, waiting for patterns to emerge, listening to the whispers of a star that has both nurtured and threatened since the first breath of life. For in its light lies survival, and in its storms lies the reminder that no fortress, no machine, no empire is beyond the reach of the sun. The Solar Dynamics Observatory, launched in 2010, marked another turning point. From its vantage point above Earth, it returned images in such exquisite detail that the sun was no longer a vague, glowing disk, but a living, boiling surface alive with turbulence. Ultraviolet eyes revealed storms unfurling like curtains of flame, magnetic arcs vaulting thousands of kilometers above the surface before collapsing back into themselves. Each day brought terabytes of data, a firehose of information that revealed beauty and menace in equal measure. Scientists stared into this torrent and began to glimpse the hidden choreography of solar storms. Though the rhythm remained elusive, the code still incomplete. To supplement this perspective, the Stereo mission to spacecraft launched in 2006, offered vision from multiple angles. Like eyes set wide apart, the twin craft observed the sun in stereo, reconstructing the three-dimensional structure of its eruptions. For the first time, humanity could follow a coronal mass ejection from its birth on the surface to its expansion across interplanetary space. The result was astonishing. A solar storm was not a single wave of energy, but a complex, evolving cloud of plasma and magnetic fields, twisting and reshaping as it raced toward Earth or swept harmlessly past. These revelations shattered the simplicity of earlier models, but they brought science closer to realism, to grasping storms as they truly are, not as crude diagrams once suggested. Yet even with these marvels, forecasting remained fragile. Earthbound meteorologists could predict a hurricane's path days in advance. Space weather forecasters were often left with only hours of warning. A flare might erupt, its energy striking Earth at nearly the speed of light, and there would be no time to prepare. A coronal mass ejection might take a day or two to arrive, but its magnetic orientation, the crucial factor in determining whether it would cause minor auroras or a devastating blackout, remained unknowable until it collided with Earth's magnetosphere itself. Humanity could see the storm coming, but could not know how hard it would strike. This limitation weighs heavily on those tasked with protecting the technologies upon which civilization now depends. Satellites in orbit cannot simply be switched off. Power grids cannot be shut down for days at a time, and navigation systems cannot be paused without consequence. The fragility of this infrastructure is a reminder that progress has not made humanity invincible, only more vulnerable. Each year, the lattice of dependency grows denser. Every plane that flies, every ship that sails, every transaction that clears across digital networks relies on signals whispered down from space. A single solar storm, striking at the wrong moment, could ripple through that lattice like a fracturing glass. The challenge of prediction lies not in a lack of data, but in the overwhelming complexity of the sun itself. Its magnetic fields twist and writhe like invisible serpents, guided by turbulent flows beneath the surface that no telescope can see. The dynamo of the sun, the mechanism that generates its magnetic cycles, is buried deep in its interior, inaccessible to direct observation. Helioseismology, the study of solar vibrations, offers hints. Sound waves echoing through the sun's body reveal currents and flows hidden within. But these echoes are faint, their messages partial, and they do not yet yield the clarity required to predict the exact moment of a storm. For forecasters, this means working with probabilities, not certainties. They map the likelihood of eruptions, estimate their trajectories, and warn of potential hazards. But the sun remains capricious. Sometimes a flare erupts from a region that appeared quiet. Other times, a vast sunspot brimming with magnetic energy rotates across the disk, yet nothing erupts at all. The sun obeys laws of physics, yet from humanity's perspective, it seems to act with a will of its own, a reminder that knowledge is not mastery. The deeper question, whispered in quiet halls of research institutions, is not merely how to forecast the next storm, but whether true prediction is even possible. The sun is a star, its processes chaotic, governed by turbulence and nonlinear dynamics that may resist any precise forecast. At best, scientists may learn to anticipate conditions, to say when a storm is more likely, much as meteorologists describe percentages of rainfall. But the dream of absolute foresight, of knowing which flare will ignite into catastrophe, may remain forever out of reach. And so the race continues, not toward certainty, but toward resilience. Engineers design spacecraft with hardened electronics, grids with protective switches, and satellites with orbits calculated to minimize exposure. These measures are not solutions, but shields, fragile barriers against forces far older than civilization itself. Each new satellite launched to watch the sun is a sentinel in that defense, a guardian offering humanity precious hours of warning. The missions of tomorrow, from ESA's solar orbiter to next-generation probes, promise sharper vision, closer approaches, and more daring encounters with the sun's breath. But even these will not silence the mystery, for in every image sent back, in every eruption recorded, there remains a shadow of ignorance. Humanity now sees the storms in exquisite detail, yet the heart of the sun remains veiled. Its cycles turn as they always have, indifferent to human fears, immune to human progress. The question is not whether another great storm will come, but when, and whether, when it does, the species that has built towers of glass and webs of light across the earth will be ready to endure it. The early investigations laid the foundation. They built the networks, launched the missions, and gathered the data. They transformed the sun from a symbol of constancy into a dynamic and dangerous force. But they also opened the door to an unsettling truth that the most vital star, the source of life itself, is also the greatest threat. The race is not against the sun, it is against time, against complacency, against the fragile belief that the universe can be tamed. The idea of a superflare is not born from imagination, but from starlight itself. Astronomers, peering into the depths of the galaxy with space telescopes like Kepler, have witnessed stars almost indistinguishable from the sun erupt with energies so vast they make the Carrington Event seem like a spark struck from flint. These stellar explosions, recorded as sudden and overwhelming brightenings, unleash forces up to 10,000 times greater than the most powerful solar storm known to human history. A single superflare could hurl enough radiation and charged particles to cripple entire planetary systems, reshaping their environments in an instant. The question lingers, hauntingly unresolved. Could the sun, the giver of life, one day betray its calm facade and unleash such a fury upon Earth? Theoretical astrophysics does not dismiss the possibility. Models of stellar magnetism reveal that under certain alignments of tangled fields, even a middle-aged star like the sun may be capable of erupting with catastrophic violence. And though no such event has been recorded in the span of human memory, the scales of cosmic time dwarf the brevity of civilization. What has not happened in 5,000 years of written history may still lie ahead, waiting in the rhythm of millennia. If such a storm were to strike, the consequences defy simple description. Simulations created by research teams at institutions like NASA's Goddard Space Flight Center sketch chilling possibilities. A superflare's electromagnetic pulse could fry satellites in orbit, burn out power grids across continents, and erase communication networks in moments. The auroras would not merely dance at high latitudes. They would bleed into the skies of every city on Earth, crimson and violet curtains of light heralding the collapse of the technological age. For weeks, months, perhaps years, humanity would struggle in the dark, cast backward into a pre-electric world. And yet, even in imagining the scale of devastation, there is a paradoxical awe. The same invisible fields that protect Earth, the geomagnetic cocoon shielding the biosphere from solar radiation, would ripple and writhe under the onslaught, struggling to contain energies never meant to be endured. For a time, it might hold, but as the storm pressed harder, the magnetic shield could buckle, inducing currents so powerful they would travel through the very veins of civilization, the wires and transformers of global infrastructure. Electricity, once harnessed as humanity's triumph, would become its undoing. At the heart of this mystery lies magnetohydrodynamics, the science of charged fluids in motion. The sun's plasma is a sea of electrons and protons, conducting electricity on scales beyond comprehension. Its magnetic fields twist and snap like ropes under unbearable strain, releasing energy through reconnection events that drive flares and coronal mass ejections. These processes, though governed by physical law, are embedded in chaos. Small instabilities can cascade into vast upheaval. A subtle shift deep within the sun's convection zone can ripple outward into storms of planetary consequence. Here, the mathematics of turbulence meets the abyss of uncertainty, and prediction becomes as fragile as a candle flame in the wind. Chaos theory teaches that deterministic systems, those governed by precise rules, can still behave unpredictably if they are sufficiently complex. The sun is the epitome of such complexity. Billions of tons of plasma boiling, magnetic fields twisting into knots, waves echoing through its interior. To model it fully would require not just supercomputers, but perhaps an entirely new physics. This is why forecasts remain uncertain, and why the spectre of a superflare haunts both scientists and philosophers alike. The probability may be low, yet the consequences are so extreme that the possibility cannot be dismissed. In this recognition lies a profound tension. Humanity stands at the pinnacle of advancement, a civilization woven together by satellites, microchips, and global networks of fragile silicon. Yet it has never been more dependent on forces beyond its control. The ancients worshipped the sun as a god because they saw its dominance over crops, seasons, and survival. Modernity, armed with physics and telescopes, has stripped away the mythology, but in doing so, it has revealed something even more humbling. The sun's power is not just a metaphor for divinity. It is a real, physical threat that dwarfs all weapons ever forged by human hands. Thus, the paradox becomes clear. Civilization has never been more advanced, yet never more fragile. Nuclear arsenals, chemical stockpiles, and industrial machinery pale beside the silent threat suspended 93 million miles away. Unlike human conflicts, the sun's fury carries no intent, no malice. It is simply the expression of natural law on a scale too vast to tame. Humanity's survival depends not on control, but on resilience, on preparing for storms that cannot be prevented, only endured. And so scientists study distant stars, measure solar cycles, and refine their models of plasma dynamics. They do so not merely out of curiosity, but from a recognition that the greatest danger may come not from within, but from above. Each flare recorded on a distant star is a mirror held to the future of the Earth, a reminder that cosmic peace is not guaranteed. The sun may remain calm for centuries, or it may, in some unknown decade, release a storm that reshapes civilization itself. The extreme edge of science is not simply about physics or equations. It is about confronting the fragility of existence in a universe both beautiful and indifferent. The sun, radiant and life-giving, holds within it the seeds of devastation. Humanity's task is not to fear, but to understand, to prepare, to adapt, and to remember that the very star that nurtures life also reminds it of its place in the vast and unpredictable cosmos beneath the surface of modern science. Clues linger in the geological record, written in the quiet ink of isotopes and ancient ice. Researchers studying cores drilled deep from Greenland and Antarctica have uncovered thin layers of radioactive particles, spikes in carbon-14 and beryllium-10, anomalies that cannot be explained by earthly processes alone. These chemical fingerprints point to events in the sun's past, sudden bursts of radiation that flooded the Earth with energy far beyond the familiar rhythms of the solar cycle. One of the most striking signatures comes from around the year 774, when trees across the globe recorded a dramatic surge of carbon-14 in their rings. No known supernova or cosmic event fits the evidence. The simplest explanation, unsettling in its implications, is that the sun itself may have produced a flare or storm vastly more powerful than anything observed in modern history. If true, then the sun has already demonstrated its potential for outbursts far greater than the Carrington Event, and if it has happened once, it may happen again in the face of such evidence. Scientists have turned to distant stars as natural laboratories. With the Kepler Space Telescope, astronomers catalogued thousands of sun-like stars, many of them flaring violently in superflares of unimaginable scale. These stars, not fundamentally different from our own, teach a sobering lesson. The sun's comparative calm may not be permanent, but rather a fortunate phase in its long life. The statistical odds remain debated, but the possibility hangs like a shadow over the future. It may not happen in a century or in 1,000 years, but on cosmic scales, even such vast intervals are but the blink of an eye. And yet, the most haunting consequence is not simply technological collapse, but the psychological shift it would impose. A civilization that sees itself as master of nature would suddenly confront its vulnerability to the cosmos. The skies above, once regarded as symbols of beauty and wonder, would become a reminder of fragility. The auroras stretching across the equator would be dazzling, but they would illuminate a world plunged into silence. Theoretical research into magnetohydrodynamics, the science of plasma and fields, continues to probe the edges of prediction. Supercomputers simulate the tangled braids of magnetic loops in the sun's corona, where reconnection sparks storms. Yet even with these tools, chaos theory whispers its warning. Complexity resists perfect foresight. The sun's surface, boiling with plasma, is a theater of turbulence where tiny fluctuations cascade into storms of colossal force. Humanity may one day improve its ability to forecast hours or days in advance. But the deeper question remains unanswered. Can a superflare be anticipated? Or is it destined to arrive without warning, a celestial ambush in the quiet of an ordinary day? In this tension, philosophers and scientists alike glimpse a reflection of the human condition. Civilizations rise, convinced of their permanence, only to be humbled by forces beyond their reckoning. Just as ancient societies bowed to droughts, earthquakes, or volcanic ash, the modern age may one day bow to fire from the sky. But unlike past generations, today's humanity is armed with knowledge, foresight, and the ability, at least in part, to prepare. Efforts are already underway. International collaborations study how to harden electrical grids, shield satellites, and store power offline to weather the storm. Some suggest building vast transformers resistant to geomagnetic surges, or placing solar sentinels, spacecraft that orbit between the Earth and the Sun, as early warning systems. Yet these measures are costly, fragile, and incomplete. The truth is stark. If a superflare arrived tomorrow, civilization would be caught unready. This is the paradox at the extreme edge of science. Knowledge illuminates the scale of the danger, yet also underscores the limits of control. The sun remains indifferent, its cycles continuing as they have for billions of years. Humanity may be capable of splitting atoms and sending probes to the edge of the solar system, but it cannot tame the heart of a star. The most it can do is adapt, build resilience, and accept the humility that comes from living in the shadow of a force both nurturing and destructive. Thus, the study of superflares is more than astrophysics. It is an existential meditation. The sun, eternal in myth, is revealed as unstable in truth. Life owes everything to its warmth and light, yet one day its fury may sweep away the fragile lattice of civilization. In contemplating this possibility, science does not merely measure plasma or magnetism. It measures humanity's place in the cosmos, a reminder that even at the height of knowledge, we remain as vulnerable as the first stargazers who once looked upward in awe and fear at the heart of the sun, where pressures rise to more than 250 billion. Atmospheres and temperatures climb beyond 15 million degrees. Hydrogen nuclei fuse into helium, releasing the energy that sustains life on Earth. This nuclear furnace is steady, its output balanced by forces of gravity and radiation. Yet the calm we see from 93 million miles away hides a more turbulent truth. The sun's surface is no placid sphere, but a roiling sea of plasma, a conductor of electricity on scales beyond comprehension. In this ocean, magnetism is the unseen master, threading through the convective motions, twisting, tangling, and building toward eruptions that can shake the solar system. Mainstream solar theory, refined over a century of study, describes this duality. The standard solar model explains how nuclear fusion drives the star's steady luminosity, but it is magnetism, born from the dynamo of charged particles circulating in the sun's vast interior, that governs its storms. Scientists have come to understand that the magnetic field is not fixed but cyclical, waxing and waning in an 11-year rhythm. During solar maxima, sunspots proliferate across the surface, dark islands where magnetic fields pierced upward. These are not calm blemishes, but the birthplaces of chaos. Regions where loops of plasma arch thousands of miles into space, storing energy like compressed springs. When the fields snap and reconnect, they unleash flares of blinding radiation and hurl vast clouds of charged matter outward coronal mass, ejections that can dwarf the Earth itself. It is in this magnetic reconnection that the sun reveals its fury. The process is as simple as it is devastating. Lines of magnetic force, twisted until they can no longer hold, break and realign, releasing energy equivalent to billions of nuclear bombs in moments. Light races outward at the speed of causality, while slower clouds of plasma surge into interplanetary space. These coronal mass ejections, traveling at millions of kilometers per hour, do not simply vanish into the void. They plow through the solar wind, carving shockwaves, compressing, and reshaping the invisible environment through which planets orbit. When such a cloud intersects with Earth, the outcome depends on alignment. If the solar storm's magnetic field opposes our own, the two fields merge, opening cracks in the magnetosphere. Through these breaches, torrents of charged particles stream downward, colliding with atmospheric molecules to paint auroras in green, red, and violet across the sky. Yet the same process that creates this beauty also carries danger. Currents surge through satellites, through high-altitude circuits, and even into the power lines stretched across continents. A Carrington-scale event, should it occur today, would test not only our instruments but our civilization's resilience to understand the likelihood of such storms. Scientists have built statistical models, combing through centuries of data. The Carrington Event of 1859 is not an isolated tale, but part of a broader pattern. Records of geomagnetic storms reveal cycles of intensity, rising and falling with the solar rhythm. Probability models suggest that an event of Carrington scale has a significant chance, perhaps as high as 10%, of occurring within a given century. Less extreme storms strike more often, their impacts already recorded in disruptions to satellites and power grids in recent decades. The question is not whether the sun will erupt again, but when. Earth's shield, the magnetosphere, remains the final line of defense. This invisible cocoon, generated by the planet's molten core, stretches tens of thousands of kilometers into space, deflecting most of the solar wind. Yet its protection is not absolute. Like a fortress under siege, it bends and strains, absorbing impacts, sometimes yielding under pressure. During the great storms, the magnetosphere compresses to a fraction of its usual size, exposing satellites and astronauts to heightened danger. Its fragility underscores a sobering truth: all life on Earth rests upon this hidden barrier, a shield that has preserved the biosphere for billions of years, yet one that can be overwhelmed in hours by the fury of its parent star. For the scientists who chart these cycles, the work is more than academic. Agencies such as NASA and ESA maintain fleets of solar observatories: the Solar and Heliospheric Observatory, the Solar Dynamics Observatory, and most daringly, the Parker Solar Probe, instruments built to watch, measure, and decode the sun's behavior. Their findings refine the Standard Model, confirming the broad outlines of fusion, convection, and magnetism, while revealing just how much remains unresolved. The sun may follow cycles, but its storms are not bound by predictability. Each eruption is a reminder that science, though powerful, can only peer into probabilities, not certainties. Thus, the mainstream understanding of the sun is both illuminating and humbling. It paints a picture of a star governed by laws of physics, its rhythms charted and its storms explained. Yet it also exposes the narrowness of control. Prediction can extend hours or days ahead, but no further. The cycles of activity may be known, but the exact moment when magnetic loops will break remains hidden in chaos. Humanity's shield, the magnetosphere, is resilient, but not unbreakable. And so the study of the sun becomes not only an inquiry into astrophysics, but a meditation on fragility, how a civilization of immense strength rests upon defenses as delicate as the dance of fields and plasma. 93 million miles away, the closer humanity looks at the sun, the more the simplicity of the Standard Model gives way to profound complexity. The nuclear heart of the star is steady, yes, but the turbulent layers above behave like a living entity, breathing, shifting, and releasing energy in patterns that defy easy prediction. The photosphere, a seething surface of plasma, flickers with granules the size of countenance, each rising and falling in cycles lasting mere minutes. Above it, the chromosphere flares with spicules that surge thousands of kilometers into space before collapsing again, while the corona, the sun's ethereal outer atmosphere, glows mysteriously hotter than the surface beneath it, a paradox that still unsettles physicists. The mainstream model explains much, but mysteries remain threaded through every layer of the star. Asterisk. The mechanism at the center of these eruptions, magnetic reconnection, has become one of the most studied yet. Enigmatic processes in plasma physics, observations from missions like the Solar Dynamics Observatory revealed the drama unfolding above sunspots. Towering loops of plasma snap and reform in fractions of a second, converting stored magnetic tension into heat and radiation. The laws of magnetohydrodynamics describe this process in equations, yet simulations still struggle to capture the scale and speed of events. On Earth, experimental plasma devices have recreated miniature reconnection events, but none compare to the ferocity of those on the Sun, where magnetic fields extend across millions of kilometers. When these reconnection-driven outbursts hurl plasma into space, the clouds travel as coronal mass ejections. They expand outward like invisible tsunamis, carrying billions of tons of charged matter. Some dissipate harmlessly into the void, but those aligned with Earth pose profound risks. As the shock wave sweeps across interplanetary space, it accelerates particles to near light speeds, creating storms that ripple ahead of the main cloud. These particles can fry the electronics of satellites before the bulk of the ejection even arrives. Hours or days later, the CME itself slams into Earth's magnetosphere, compressing and distorting the shield. Magnetometers on the ground record the impact as sudden, global jolts, geomagnetic storms whose strength can cripple modern infrastructure. To anticipate these dangers, scientists have built probability models grounded in centuries of data. The Carrington Event of 1859 remains the benchmark. A storm so intense that telegraph wires sparked into flames and auroras were visible as far south as the Caribbean. Modern analyses suggest it was a 1 in 500-year event, though more modest storms occur on decadal timescales. A major storm in 1921 and another in 1989, which plunged Quebec into blackout, remind researchers that even mid-range events can test our resilience. Statistical studies now suggest a 1 to 2% annual chance of another Carrington-class storm. That may seem small, but over decades it becomes a near inevitability. The sun is patient, and time is its ally. Earth's magnetosphere stands as the bulwark against these cosmic assaults. It stretches like a teardrop into space, compressed on the day side and trailing vast streams behind. Without it, the solar wind would strip Earth's atmosphere as it has done to Mars, leaving the surface barren and exposed. Yet the shield is not unshakable. Strong storms compress the magnetopores to altitudes where satellites orbit, directly exposing them to particle flux. Currents induced in Earth's crust and oceans during these disturbances infiltrate power lines, pipelines, and communication systems. A civilization laced with electronics, with a nervous system of satellites, is uniquely vulnerable to the sun's storms in a way that earlier centuries were not. The paradox becomes clear. Progress has given humanity immense capability, but also greater fragility. To guard against this vulnerability, agencies have expanded their vigilance. The Parker Solar Probe now dives closer to the sun than any spacecraft in history, sampling the solar wind at its source. The European Solar Orbiter traces orbits that tilt above the sun's poles, regions thought to anchor the magnetic cycles. These missions refine the Standard Model, revealing how streams of plasma emerge, how fields twist, and how the cycle evolves. With every close pass, Parker gathers data that could one day sharpen forecasts of solar storms from vague probabilities to precise warnings. Yet even the most advanced models admit a limit. Chaos is embedded in plasma physics, and the timing of reconnection events may remain forever beyond exact prediction. And so, mainstream science paints a portrait that is both confident and humble. The sun is understood as a nuclear furnace, its surface shaped by convection, its magnetism driving storms. The solar cycle is measured, the probabilities modeled, the shield of Earth described. But beneath this confidence lies an acknowledgement. Humanity lives within the margins of a fragile protection, subject to events that can be explained but not controlled. The clock of the sun ticks steadily, yet its alarms are unpredictable. Reminders that our world is not insulated from the vast forces of its star. It is this interplay of knowledge and uncertainty that gives the mainstream model its paradoxical weight. The sun is familiar, yet unfathomable. It is studied daily, yet capable of surprises that can reshape civilization. Humanity's shield holds, but not without strain. And always, silently, the question lingers. When the next great eruption comes, will preparation meet reality, or will the star that gives life remind its orbiting world how fragile its light-born civilization truly is? They call it the speculative frontier, a boundary where science leans forward into the unknown, where theory stretches its fingers toward mysteries that may or may not ever be proven. It is here, at the edges of solar physics, that bold ideas rise, sometimes dismissed as fringe, sometimes whispered as warnings. For even if unproven, they carry with them the weight of possibility, and possibility is enough to haunt. One of the most unsettling ideas is the superflare hypothesis. Observations of stars, like our Sun, ordinary yellow dwarfs, scattered across the galaxy, reveal eruptions far beyond anything ever recorded in human history. Telescopes such as Kepler have caught the signatures of flares thousands of times more powerful than the Carrington Event. Storms that would not merely disrupt satellites, but strip the atmosphere of a planet if unleashed too often. The question that follows is disquieting. Could our own star, steady for billions of years, harbor the capacity for such fury? Most mainstream models suggest that the Sun is too stable, its rotation too slow, its magnetic field too balanced to trigger these cataclysms. Yet the scars seen on distant stars insist that nature does not always follow rules of comfort. Rare alignments of magnetic fields, strange instabilities deep in the convection zone, these are enough, some argue, to awaken a hidden potential. A single such event could erase centuries of progress in a single day. Others venture further, imagining not isolated eruptions but chain reactions across the solar surface. Magnetic storms, usually confined to regions of sunspots, could, in theory, cascade across hemispheres, like a wildfire leaping from one dry forest to another. Plasma loops reconnect, fields collapse, and the energy multiplies with every step, until the Sun's entire face becomes a canvas of violence. The likelihood remains speculative, but computer simulations suggest that such domino effects are not impossible. If so, the quiet assumption that solar storms remain regional may be a dangerous illusion. Beyond the Sun itself, some theories gaze outward, toward the wider cosmos. Could the rhythms of solar activity be influenced by forces greater still? Some astrophysicists have wondered if our star's behavior is subtly guided by its orbit through the galaxy. The solar system drifts through arms of interstellar dust, regions richer in cosmic rays, or even dark matter clouds invisible to the eye. Such environments might subtly alter the magnetic scaffolding of the Sun, nudging it toward instability. It is speculation, yes, but speculation born from patterns, hints that solar cycles do not always follow their expected timing, that grand minima and maxima appear as if triggered by invisible tides. There are those who even ask if solar tempests have altered the course of Earth's history itself. Geological archives tell of sudden climate disruptions, spikes of carbon-14 in tree rings, isotopic anomalies buried in ice cores. Some of these signatures align eerily with evidence of solar outbursts. Could ancient extinctions, sudden collapses of ecosystems, or shifts in human civilizations have been catalyzed not by earthly causes alone, but by storms of light and magnetism from the star above? It is not proven, but it remains a haunting thought that the fate of species, perhaps even the rise and fall of empires, has been swayed by forces no one alive could see, only feel in the aftermath. Fringe though it may sound, correlations between solar cycles and human behavior have long been studied at the margins of science. Records of stock markets, wars, creativity, and unrest have been loosely compared with sunspot data. Most dismiss these as coincidences, the product of pattern-seeking minds. Yet the possibility that cosmic rhythms might subtly influence biology or psychology through geomagnetic fluctuations that touch brain chemistry or circadian cycles is not entirely dismissed. Even if tenuous, the idea carries philosophical weight. If humanity is influenced, however faintly, by the pulse of its star, then our autonomy may be more fragile than believed. At the edge of all these theories lies a larger reflection. The Sun, giver of life, may also be a quiet reminder of mortality, not only personal, but planetary. Its storms are not moral, not intentional, yet they echo like warnings in the silence of space. They remind the orbiting world that fragility and grandeur are bound together. The same star that paints dawn and nourishes forests carries within it the possibility of civilization's undoing. To contemplate this is to feel both awe and humility. The speculative frontiers of solar science continue to unfurl like layers of a mystery that refuses to be solved. Each question answered seems to spawn two more, each observation a reminder of how much lies hidden within the luminous furnace above. For centuries, humanity has charted the sun's surface with care, tracking its rhythms as if recording the heartbeat of the cosmos itself. Yet in the faint irregularities, in the anomalies that do not fit the standard model, scientists glimpse the possibility of forces deeper and stranger than imagination first allowed. The superflare hypothesis stands as the most haunting of these. Its foundation rests on a simple observation. If stars nearly identical to the sun can unleash cataclysms magnitudes greater than any solar storm in recorded history, then why should our star be exempt? The answer has never been conclusive. Some argue the sun's relatively gentle nature is the product of its slower rotation, its mature magnetic structure, a sign that youth's violence has long passed. Others insist that stability does not imply safety, only rarity. A single rare alignment of magnetic fields, a sudden surge from deep within the convection zone, could break the rhythm of centuries. It has not happened in the age of radio, satellites, or digital networks. But absence in history is not the same as impossibility. If such an eruption occurred, simulations suggest its aftermath would be unlike anything humanity has endured. Global electrical grids would collapse under induced currents, transformers burning beyond repair. Satellites, the nervous system of modern life, would flicker and fail, their circuitry fried by invisible surges. Even pipelines buried underground could melt from currents flowing like rivers of fire beneath the soil. Within days, silence would fall over networks that once hummed with constant connection. The world would be thrust into a paradox. The most advanced civilization reduced to something resembling the pre-industrial, not by war or collapse of politics, but by the unseen hand of its star. Some theorists extend this unease with a notion of cascading solar reactions. They propose that the sun's tangled magnetic fields, usually localized, could one day chain together in an event far more global. What is now confined to isolated active regions might instead leap across hemispheres, forming a storm system not of clouds and rain but of plasma arcs spanning millions of kilometers. Each reconnection event would feed the next, a runaway cascade releasing energy on scales unthinkable. It is a theory still debated, but in the language of magnetohydrodynamics, it cannot be dismissed outright. For if chaos defines plasma, then perhaps chaos one day could link the entire surface in a single, synchronized storm. Speculation also wanders beyond the sun itself, toward cosmic influences unseen. The solar system drifts in its slow orbit around the Milky Way, crossing regions dense with interstellar dust, cosmic rays, and perhaps even veils of dark matter. Could these invisible seas influence the sun's stability? Some astrophysicists note that cycles of unusual activity seem to align, however loosely, with the system's passage through galactic arms, where gravitational and energetic conditions differ. If true, the sun may not be an isolated engine but a participant in galactic tides, its behavior stirred by forces stretching across thousands of light-years. The evidence is thin, but the idea lingers, that stars themselves are not entirely autonomous, but subtly shaped by the larger ocean of the galaxy. This raises an unsettling thought. If external conditions can magnify or suppress solar activity, then the sun may be less predictable than once hoped. Forecasting cycles may be akin to predicting waves on a sea without knowing the depth of the ocean beneath. Every irregularity in tree rings, every isotope spike in ice cores, Every unexplained anomaly in cosmic ray data becomes a whisper, suggesting that history may carry hidden signatures of solar extremes, lost to memory but imprinted in nature. Some researchers have dared to look at humanity itself in this mirror. Records hint at curious coincidences, surges of unrest, revolutions, bursts of creativity, or strange rhythms in economics appearing to align loosely with sunspot cycles. Most dismiss these as numerology, the desperate matching of unrelated patterns. Yet beneath the dismissal remains a kernel of intrigue. Could fluctuations in geomagnetic fields influence human biology at the margins, circadian rhythms, serotonin levels, perhaps even collective mood? The evidence is fragile, scattered, more philosophy than physics. But the possibility that cosmic storms ripple not only through machinery but through minds adds a new dimension to the story. It suggests that humanity's bond with the sun may not be purely physical, but faintly psychological, a subtle tether tying inner states to stellar rhythms. Speculation then becomes less about prediction and more about perspective. Even if the more extreme theories remain unproven, they force a confrontation with scale. The sun is not just a glowing sphere in the sky, nor only a calculable engine of fusion. It is a star among stars, bound by the same cosmic rules that govern galaxies and clusters, capable of wonders and terrors beyond the reach of easy certainty. Its storms may be rare, its extremes perhaps unlikely, but their very possibility reframes humanity's relationship with its own existence. At the heart of this lies philosophy as much as science. The sun, once worshipped as a god, then reduced to equations of fusion, now rises again as a reminder of fragility. Whether its most violent possibilities come to pass or not, the fact they could is enough. For in that fragile uncertainty, humanity finds humility, the recognition that the sky above, so constant in its warmth, also harbors the capacity for silence, darkness, and fire. And to live beneath it is to live at the mercy of forces as ancient as time itself. The modern age of solar science stands upon a threshold of vigilance. No longer is the sun observed only as a giver of light and warmth. It is now monitored as a potential adversary, a star whose moods must be tracked with the precision of a watchman pacing the walls of a fragile city. Across Earth and beyond its atmosphere, instruments gaze unblinkingly at the solar surface, each one built to capture a whisper of warning before the silence shatters into a storm. High above, in a looping path that draws it closer to the furnace than any craft before, NASA's Parker solar probe braves a realm once thought unreachable. Shielded by carbon composite plating, it sails through the sun's corona, the ethereal crown of plasma that surrounds the star. There temperatures rise to millions of degrees, hotter even than the surface below, a paradox that has challenged physics for decades. Each pass yields fragments of truth, particles streaming outward at speeds of hundreds of kilometers per second, magnetic fields twisting into serpentine forms, shock waves born of eruptions still racing outward. What Parker sends home is more than data. It is the first direct touch of humanity upon the edge of a living star, further from the inferno, yet close enough to witness details with exquisite clarity. The European Space Agency's solar orbiter turns its lenses toward the sun's poles, regions long hidden from Earth's perspective. Here it is, magnetism that is sought, the grand loops and arcs that weave the solar cycle. To map these fields is to peer into the invisible machinery that drives flares and eruptions. For the first time, humanity is not merely recording what the sun has done, but attempting to glimpse what it may do. The dream is to forecast storms, not hours in advance, but days. Perhaps weeks, enough time to move satellites into safe modes, to reroute flights, to brace power grids for impact. on the slopes of Haleakala in Hawaii. The Daniel K. Inouye Solar Telescope stands like an eye of fire against the sky. Its mirror, more than 4 meters across, gathers sunlight not to warm but to dissect. With it, astronomers can resolve details on the solar surface as small as 20 kilometers across, each sunspot and filament revealed in intricate texture. It sees the sun not as a distant disk, but as a restless ocean, granules of boiling plasma rising and falling in waves of convection. The telescope captures the raw materials of space weather, the roots of storms before they erupt into space. This triad, Parker brushing the corona, solar orbiter mapping the poles, and Inouye resolving the smallest scales of turbulence, forms a new kind of constellation. Alongside them orbit veterans like SOHO and the Solar Dynamics Observatory, satellites that keep watch with uninterrupted vigilance, relaying real-time images of the sun's face to command centers on Earth. Together, they represent an unprecedented effort, a planetary defense not against missiles or asteroids, but against the very star that sustains life. Yet the work is not solitary. Across nations, agencies collaborate in networks that share both data and concern. The Space Weather Prediction Center in the United States, the European Space Agency's heliophysics programs, Japan's Hinode mission, India's Odditil 1, all feed into a growing web of vigilance. The recognition has dawned that no single nation can shield itself alone. A storm of sufficient scale would be global by nature, its consequences indifferent to borders or politics. In this sense, space weather readiness may be the first true planetary defense system, one that unites not in the face of human conflict, but in shared vulnerability to the heavens. In this uneasy balance lies the paradox of humanity's progress. The instruments grow ever sharper, the collaborations broader, the models more sophisticated, and yet the question remains: when the sun unleashes its next great storm, will the preparation prove enough, or will it be revealed that even foreknowledge is not defense, that the fire above can never truly be tamed? Thus the gaze continues, unbroken and unblinking. The telescopes watch, the satellites orbit, the probes dive. Each observation is a note in a symphony of vigilance, each warning a fragile barrier against catastrophe. And through it all, one truth endures: the sun is both protector and predator, and the line between its gift and its wrath is measured not in centuries, but in moments. Humanity listens, records, and waits, aware that the next pulse of light may carry within it not only warmth, but warning. The pursuit of solar preparedness is a race against an adversary that does not compete, but simply exists. An indifferent force woven into the fabric of the cosmos. Humanity has built its defenses not in fortresses of stone or steel, but in observatories, algorithms, and fragile agreements between nations. The current era represents the first time in history that our species has attempted to read the language of a star with the explicit intent of self-preservation. It is a task both monumental and humbling. At the heart of this effort lies an understanding of cycles. The sun is not static. It breathes through its magnetic rhythms. Every 11 years, sunspot activity waxes and wanes, marking the transition between solar minimum and solar maximum. During maxima, the surface roils with dark blemishes, eruptions multiply, and the likelihood of powerful coronal mass ejections rises dramatically. Scientists today monitor these cycles with a precision unimaginable even half a century ago, yet prediction still slips through their grasp. Some storms emerge without herald, their power revealed only after they have already begun their journey toward Earth. This uncertainty drives the urgency of every new instrument launched, every telescope constructed. NASA's Parker Solar Probe remains the most daring of these endeavors. Each orbit brings it closer to the sun, and with each pass, the spacecraft collects torrents of information on the solar wind and the chaotic regions where magnetic fields snap and reconnect. These reconnection events are the hidden engines of solar storms, releasing energies that dwarf the combined output of all nuclear weapons on Earth. By flying into this environment, Parker is not merely observing, it is sampling the raw fuel of space weather. The probe's discoveries, the zigzagging magnetic switchbacks, the surprising acceleration of charged particles are already reshaping models of how solar storms evolve. Meanwhile, the European Space Agency's solar orbiter complements Parker's daring approach by providing perspective. Its vantage points allow scientists to chart the geometry of magnetic loops stretching above sunspots, mapping how stresses build until they rupture in explosive release. This is more than academic work. By tracking such structures, researchers hope to create the first reliable warning system, a means to identify a potential flare or ejection before it happens, not merely after. If realized, such foresight could transform the way power companies, airlines, and satellite operators prepare for solar assaults. Yet the sun is not a puzzle that yields easily. Plasma, the medium of its storms, behaves in ways that evade even the most advanced supercomputers. Unlike the predictable flows of air and water, plasma is guided by invisible fields, twisting into patterns of staggering complexity. To simulate a single eruption in full detail would require computational power far beyond today's capacities. What scientists attempt instead is to approximate, to construct models that capture enough truth to be useful, even if the full picture remains hidden. These models are tested continuously against real events, improved incrementally as each flare and storm is observed. Progress is steady, but the margin of uncertainty is never erased. On Earth, ground-based observatories like the Daniel K. Inouye Solar Telescope push in a different direction: resolution. By studying the sun's surface at the finest possible scales, they reveal the granules of plasma that churn like boiling water, the tangled filaments of magnetism that weave storms from chaos. Inouye's observations provide the foundational details, the smallest threads of a tapestry that space-based missions then contextualize. Together, they form a system of eyes that watch the sun across scales of space and time, from the tiniest turbulence to the vast arcs, stretching millions of kilometers into the void. But observation alone does not guarantee safety. For protection, humanity must build resilience into its own infrastructure. Space weather preparedness has quietly become a field of global importance. Though it lacks the visibility of more familiar threats, power grid operators conduct simulations of geomagnetic disturbances, testing how transformers would respond to surges induced by solar storms. Satellite designers explore shielding techniques and fail-safe modes, seeking ways to preserve critical communication and navigation systems when the skies ignite. International aviation authorities rehearse contingency plans for rerouting flights away from polar routes when radiation levels spike. These efforts are small threads, but together they form the beginnings of a safety net. Even so, the net is fragile. Many power grids remain vulnerable, built with little consideration for space weather. Satellites proliferate in low Earth orbit at a pace faster than protective measures can be applied, and the coordination of global response, though improving, is still uneven. A storm of sufficient scale, one echoing the ferocity of the Carrington Event of 1859, could overwhelm even the best-laid preparations. The hard truth is that humanity can mitigate, but not eliminate, the danger. What emerges from these realities is a paradox. We are more aware of the sun's behavior than at any point in history, yet still exposed to its wrath. Each new mission reduces uncertainty, but does not dissolve it. Each new model sharpens foresight, but leaves shadows untouched. Humanity is caught between knowledge and vulnerability, advancing rapidly yet never reaching safety. Still, there is a quiet triumph in the very attempt. The Parker Solar Probe, the Solar Orbiter, the Inouye Telescope, and countless other instruments embody a refusal to be passive before the cosmos. They represent the transformation of wonder into vigilance, curiosity into defense. And perhaps this too is part of what it means to be human, to stand beneath the sun, recognizing both its gift and its threat, and to respond not with fear alone, but with determination to understand in the end. The question is not whether humanity can stop the sun's storms, for it cannot, but whether it can endure them. Science, in this context, becomes less an attempt to master nature than a quest to live wisely within it. The observatories do not promise immunity. They offer awareness. An awareness, though fragile, may be the strongest shield we can raise against the fire above, beneath the eternal blaze of the sun. Humanity has long measured its existence in fragile increments of borrowed light. It is the source of warmth, of harvest, of the rhythms that shape oceans and seasons. Yet within that brilliance lies a quiet paradox. The very force that sustains life on Earth could, with one unthinking exhalation, undo the machinery of modern civilization. This truth is neither malicious nor merciful. It is indifference, wrapped in radiance. For centuries, human fears were largely of its own making. Armies marched, empires clashed, weapons grew from stone blades to nuclear arsenals capable of searing continents. The shadow of annihilation became a familiar spectre, born not from the heavens, but from the rivalries of humankind. Yet beyond those conflicts, above all banners and ideologies, the sun burned on, steady and absolute. The fire in its core is older than language, older than memory, older even than Earth itself. Compared to this furnace, the struggles of nations appear as sparks extinguished before they touch the ground. In the cold calculus of the cosmos, there is no contest between human power and solar fury. A single coronal mass ejection, launched with the violence of billions of hydrogen bombs, could cripple power grids, silence satellites, and return vast regions of the world to a prodigital state. No missile defense system could intercept it. No treaty could prevent its arrival. While humanity has built weapons designed to outmatch its own species, it has built no arsenal to shield against the star upon which all life depends. Here lies the quiet irony. The greater danger has always been silent, vast and unaltered by our existence. The ancients intuited fragments of this truth. They bowed before the sun as both god and destroyer, offering ritual to a force they could neither command nor comprehend. In temples from Egypt to Mesoamerica, the sun was carved into stone as eternal witness and judge. Its rising was salvation, its eclipse an omen. Though science has replaced mythology with equations and models, the emotional resonance remains. The sun still commands reverence, not through prayer, but through the uneasy recognition that our survival rests on the stability of a star we cannot tame. Civilization today is a lattice of circuitry, fibers, and signals, a web stretched tenuously beneath the sun's unblinking gaze. Banking systems hum with electronic pulses, aircraft cross oceans guided by satellites, hospitals rely on power as much as medicine. In this world, fragility wears the mask of strength. For all the towering skylines and glowing cities, it would take only hours of unmediated solar fire to plunge much of it into darkness. What armies could not conquer, the sun could unravel without intent. This dependence is paradoxical. Every heartbeat, every crop, every breath of oxygen owes itself to solar energy. Photosynthesis, climate, the very possibility of liquid water, all are gifts of the star. Yet to lean on such a giver is also to live with the shadow of its wrath. To speak of solar storms is to soften reality with metaphor. These are not tempests, but eruptions from a cosmic engine whose scale dwarfs imagination. Humanity lives not beside the sun, but within its atmosphere, encased by winds of plasma and magnetic storms that never cease. We are passengers in its domain, not masters. The reflection extends deeper still. What does it mean that a civilization capable of mapping galaxies, sequencing genomes, and contemplating its own origins remains so vulnerable to its parent star? It is a humbling reminder that progress does not equal invincibility. The hubris of human achievement, the belief that technology has placed us beyond the reach of nature, dissolves when measured against the reality of stellar physics. The sun does not conspire against us. It does not notice us. Yet its indifference is more absolute than hostility, and therein lies its power. Perhaps this fragility is not a flaw, but a lesson. To live in the presence of a star is to live with him. The earth itself is temporary. The sun, too, will one day exhaust its fuel and expand into a red giant, swallowing worlds. In the cosmic scale, every invention, every monument, every memory is fleeting. And yet, it is precisely in this fleetingness that meaning emerges. Awareness of fragility sharpens the will to endure. Knowledge of impermanence deepens the pursuit of understanding. So humanity watches, measures, and calculates, seeking patterns in the shifting light. Telescopes trace the scars of sunspots. Spacecraft dive into streams of solar wind. This pursuit is not only scientific but existential, an attempt to find order where none is promised. Yet the sun owes no explanations. It will continue to burn, guided by physics alone, indifferent to prayers or equations. To gaze into it is to confront a truth both terrifying and liberating. The universe is not shaped to our survival, and yet we endure within it. In the closing reflection, the image lingers, a planet wrapped in delicate circuits, spinning beneath the endless blaze. Above it, a star that is neither enemy nor ally, but a reminder that power is not always violent, that destruction may come without malice, and that survival is never guaranteed. Humanity gazes upward, searching for signs, yearning for certainty, yet in the depths of the sun there are only questions, written in fire, and still, in that fire, life continues, fragile, luminous, and aware. The fragility of civilization beneath the sun's gaze reveals not only a scientific challenge, but a philosophical mirror. To contemplate the possibility of a solar storm erasing modern technology is to confront the illusion of permanence that defines the human story. Cities appear eternal when lit at night, their skylines etched against the horizon as monuments of progress. Yet the same currents of plasma that dance upon the solar surface could render those lights silent in a matter of minutes. Beneath the vastness of stellar forces, permanence is an illusion, and fragility is truth. The ancients may have grasped this paradox in their own way. To the Egyptians, the sun was Ra, creator and destroyer, eternal in its cycle. To the Aztecs, it was a deity that demanded sacrifice, its survival linked to the offerings of human blood. These beliefs were born of fear, reverence, and necessity, but they echoed something deeper, the recognition that existence itself is a gift, bestowed by a star that might one day withdraw it. Modern science, with all its equations and spectrographs, has only reframed this ancient intuition in technical language. The worship of gods has become the study of fusion, magnetism, and plasma, but the awe remains unbroken. Within laboratories and observatories, scientists trace the pulse of solar cycles with a mixture of precision and unease. 11 years between peaks of sunspot activity may sound predictable, yet the rhythm carries mysteries. Each cycle arrives with its own temperament, sometimes muted, sometimes violent. What determines the ferocity of a given epoch? What hidden patterns lie within the sun's deep interior, churning and twisting magnetic fields like threads in a loom? Even now, with spacecraft plunging into the corona and telescopes resolving solar granules in unprecedented detail, the sun withholds its final secrets. The star we depend upon remains partly unknowable. This unknowability shapes more than science. It reshapes humanity's understanding of itself. For centuries, humans believed the sky to be a fixed canopy, predictable and orderly. The Enlightenment extended this belief into the mechanical universe, a clockwork cosmos where every motion could, in theory, be calculated. Yet the sun defies such neat certainty. Its eruptions are governed not by regular mechanics, but by chaos. Turbulent plasma obeying laws of magnetohydrodynamics, so complex they resist complete prediction. In this chaos lies both wonder and danger, reminding humanity that the universe is not a machine built for comfort, but a wilderness of energy where survival is contingent. The threat of solar catastrophe also reframes human conflict. Nuclear war, once feared as the pinnacle of destruction, is revealed as parochial in the face of stellar forces. A solar superflare would not distinguish between borders or ideologies. It would not heed treaties or honor peace. It would simply arrive, enveloping the Earth in radiation and magnetic fury, toppling satellites, shorting grids, unraveling the infrastructure that defines modern life. Compared to such impartial devastation, human disputes appear small, like quarrels beneath a looming storm. And yet, this vulnerability carries an unexpected gift. It reveals the profound interconnectedness of civilization. An event that disables satellites in orbit would ripple instantly across continents, halting communication, trade, and navigation. No nation would remain untouched. In this sense, the sun is both threat and unifier, reminding humanity of its shared fragility. The same star that nurtures life on every continent also holds the power to humble them all at once. Within that shared fragility lies the seed of shared responsibility to prepare, to understand, to endure. Preparation, however, is not simple. Engineers strengthen grids, build redundant systems, and design spacecraft to withstand bursts of radiation. But no defense can be absolute, even with warnings, even with systems hardened against the storm. A sufficiently powerful eruption would overwhelm protections. This uncertainty forces a confrontation with limits. It asks whether human ingenuity, however advanced, can ever fully master the forces of a star. It asks whether survival is about control, or about humility and adaptation. Perhaps this is the sun's greatest lesson, that control is fleeting, but awareness endures. To study its cycles, to chart its storms, to send probes into its corona, these acts are more than practical defenses. They are gestures of reverence, acknowledgments of dependence. In every stream of data returned from a solar mission lies the echo of ancient prayers, not in words but in numbers, carrying the same plea to understand, so that life may continue as humanity gazes toward its star. It sees not only physics, but itself reflected. Fragility is not weakness. It is the condition of life, and in that fragility lies resilience, the capacity to adapt, to anticipate, to endure despite uncertainty. The sun does not promise safety, but it offers illumination, a reminder that survival has always meant finding balance within forces far greater than human will. In the silence between solar storms, when the skies are calm and the grids hum quietly, civilization lives within a delicate grace, A grace that could end, suddenly, with a surge of plasma born from the depths of the star. And yet, until that moment comes, humanity endures, fragile but luminous, forever beneath the fire that gives both life and peril.